Okay, so there are, um, we've talked about a small set of chromatographic issues, namely um, what's sort of been termed the general elution problem, right? If you really have a good mixture of compounds in your sample, there's no one method, there's no one set of stationary phase, mobile phase, temperature, et cetera, that will be able to elute all of those compounds out with reasonable um, retention times, reasonable resolution, that kind of thing. And so that general elution problem, we discussed two different solutions to it, one for HPLC and one for GC. In HPLC, of course, we do gradient elution, where we don't keep the same set of conditions throughout the run. We change that the polarity of our mobile phase so that we sort of encourage those more nonpolar compounds to come off the column faster. Um, in gas phase, in GC, of course, we just use temperature programming to do that. And so we increase the temperature over time so that the compounds that adsorb onto the surface of that GC column do it better, get into the gas phase more easily at higher temperatures. So that's, again, sort of the general elution problem. But once it elutes and it comes off of our column, we will see tomorrow, likely, some issues known as peak asymmetry, which is what we're going to talk about. The most common by far is peak tailing. Remember that our x-axis here is time. And so our peak comes off at a given time, but then there's more of our analyte that sort of hangs on to the column, and that's why we get this long tail. We call this tailing. This asymmetry constant has lots of different terms depending on who you look at. There's no sort of generic standard term for it because we don't really use it a whole lot except to say that's bad or oh golly, it's really bad. And so there's not like it's useful aside from letting us know how poorly we're doing. And so this particular figure uses A sub S, and it's the tail, right? So the width of the tail, B is the tail width at 10%, and A is the tail front, we call it. I mean, sorry, the front width, not the tail front. That makes no sense. Again, ups and 5 o'clock width, 10%. Okay. The reason we use this 10% height here, this 10% refers to the height from the baseline. The reason we use that is because if we use the baseline, then it's really kind of sort of hard to tell exactly where that baseline ends and begins. You know, in this one, they have it going nice because they've just drawn it. They have it going all the way down back to the baseline at the beginning and at the end. But again, as you'll see tomorrow, your some of the baselines, you know, you'll have a peak, and then that baseline will start to just, you know, increase over time. And that happens. That really happens a lot in gradient dilution because our mobile phase is changing. And if the mobile phase absorbs slightly differently at a different ratio, then we're going to increase or decrease that background. And so, you know, we see this sometimes, but that we correct for that within a peak by taking that 10%, that width at 10% height. And so, you know, if we have very little tailing, this is say 5%, right, between 1 and 1.05, we say that's pretty good. 20% tailing, that's okay. If it's really asymmetric, we're up here at 200% tailing. That's pretty lousy. And so what are the things that can lead to this? The biggest issue is that, well, obviously, some of our analyte is hanging on to the stationary phase longer than the rest of our analyte. Right? And there are a few reasons for that. One of those main reasons is, well, let me back up just a hot minute. One of the reasons for this asymmetry are what are called hotspots in a column. These hotspots are areas in the column, in that physical surface, that are more attractive to whatever our analyte is. And so it could be for any number of reasons, but we talked a little bit about how there's this either alumina or this silica base that's been functionalized. If those functional groups break off or hydrolyze, then you can be left with just your silane, so either SiOH, or if you have a high enough pH, SiO minus, right? And so that negative charge, if it's a negative charge on a C18 column, well, all of a sudden we got this really polar spot where that negative charge is, while everything else around it is nonpolar. Right? And so our stuff is sticking to that one spot really well because that spot is polar, even though everything else around it is nonpolar. And so that hot spot, that sticky spot, keeps everything from coming out at the same time. And so we can think about these as being sticky for any number of reasons. So that was just an example where we're using a C18 column. You can imagine that if we were doing affinity chromatography, remember in affinity chromatography, that's the one where we have, say, antibodies that are bound to the stationary phase. And as the sample runs through, those antibodies hold on to whatever the antigen is that we're trying to separate out. If you do a semi-poor job of putting those antibodies on the column evenly, right? I mean, it's not an easy thing to do to make sure those antibodies are spread out across the column. If they're sort of, one region of the column is particularly saturated with those antibodies, then that part of the column is going to hold on to your antigen very well while your mobile phase pushes the rest of the antigen through. And so, whatever type of stationary phase we're talking about can have these hot spots, these sticky spots. Okay. Another thing that we sometimes have to deal with when we talk about fronting and tailing is if we have a sticky spot and one analyte from a previous run hasn't left that spot, right? And so we could have reactions that are happening on the column, interferences, from previous analyte, interferences, reactions. And so it could either be, reactions with something that's left over if we didn't flush long enough, or if we're just, if it's auto sampling and we're going between run to run to run, or, if whatever our analyte is reacts with whatever the column is made of, right? If that stationary phase, let's say again that silane is ionized, and so it's a negative, and our molecule has a positive charge. Well, it could be that those two are, really reacting together, and depending on the compounds, they could even form covalent bonding with the column, and that's an issue, right? Obviously. So how do we correct this? How do we think about peak tailing? Well, so this dark black line here is the surface of our particle that is being functionalized. These are C8 columns, you can tell, because there's 8 carbons in a chain here. And so even though that surface has been functionalized, there's still plenty of unfunctionalized silane groups. And so if we're operating at a too high of a pH, those can actually, sort of break off, and we just get this O minus. And these O minuses will interact with whatever positively charged thing we have. And so if we operate at a lower pH, we will protonate the column and not that an OH group is a whole lot less polar than an O minus group, but it's going to have slightly lower, slightly less, slightly weaker interactions with our analyte. And so we still have that issue of it being slightly polar, but it's not going to be as strongly bound to the analyte as the analyte comes through. A deactivated column, highly deactivated, is kind of a, from my perspective, it's kind of oxymoronic, right? Because the more deactivated a column is, it actually has more of the stationary phase we're interested in. Right? What's being deactivated are those silane sites, and you're replacing those with, either your stationary phase or with this, you're capping it with this silicon tetramethylsilane, CH33SI. And so going from here to here, right, obviously we have lowered the pH. This is that first one, because we protonated those oxygens. But if we had a highly deactivated column, all of these OHs would be these silicon tetramethyl silicons. And so you just go through and you add extra tetramethylsilane to it to react with all of those OH groups that are left over. And there are instances where you can do this sort of, I want to say in vitro, but that's not exactly what I mean, in situ, where once you've run the column for a while and you've maybe stripped off some of these groups, you can apply a little extra TMCS, tetramethylchlorosilane, and then you have this little thing where the chlorine goes away and it reacts with the oxygen. I'm not an organic chemist, whatever. But you have this, you can sort of cap your OH groups. And so these two are, column issues. Well, this one is too. I don't know. I got a little out of order when I put these in here. This is also a column issue. If you have some kind of blockage, so we talked a little bit on Tuesday when we ran our capsaicin and we took off that surfactant column. That surfactant column had a little guard column on the front side of it, right? I mentioned that guard column was just to prevent solids or um, compounds that would react with that column from getting into the main column. Um, and if you don't have a guard column and you have this column bed deformation, so the column bed is those particles that have been functionalized with our stationary phase, right? And so this column bed, so these are those silica or alumina particles that our stationary phase is bonded to. So that's, this dark red, this dark black part here is our column bed. So if we have a deformation, either, literally a chunk has been taken out of it, which is rare and hard to do. Maybe somebody dropped the column on the floor before they put it in the instrument, and so it broke or something like that. The other option is that you have sort of clogged up one or more of the pathways through that column. Remember, in the Van Deemter equation, we talked about how the different paths that things can take affects the number of theoretical plates and the plate height. If we have stuff that has actually clogged some of those pathways, then we are sort of falsely increasing the path length, but only for those particles that enter the column in that region. I need an extra slide. Hang tight. I know, screen sharing has stopped. I need more white space. Okay. One more again. So you can imagine if we're looking at the end of the column. So remember, this is really like 5 millimeters or something. But we're looking at the end of the column, and say that you have somehow managed to get some goo on the end of the column that sort of covers up this part of it, right? This part of your column has gotten gungy. Well, it sort of casts this shadow down the column, right? Where, because no particles can enter from that direction, they can't really populate that region of the column, right? And so any particles that come in, remember from our sample, I'm just going to draw our sample is coming, and every part, it's hitting the face of that column at every part. But those analytes that hit in this region have got to work their way around and then diffuse back into the column, right? They've got to somehow get out of the way of that blockage, and then diffuse out of the column. And so the fraction of the analytes, or the fraction of the sample, that was not my accent. I don't know who that was. That's blocked must spend extra time moving around whatever that blockage is. So not the whole column is blocked, and so it's not like our whole peak disappears, right? Only part of that column is blocked, and so only part of our analyte is slowed down and ends up tailing. And so this fraction is in that long tail. Okay. And so that's what they mean by column deformation. You actually have some obstruction in the column that some fraction of the analyte has to work its way around, lengthening the path that particular analyte has to take, and therefore the time that it takes for that sample, that particular analyte molecule to work through the column. Okay. All right, let me jump back for just a minute. So that was this one. We moved him up there. So mass overload in sample cleanup. Mass overload, as it sounds, is when you just put too much analyte on the column. Right? When you put too much analyte on the column, the vast majority of it flows through because the actual stationary phase is saturated. It doesn't have anywhere to go, and so it just moves through quickly. Right? And so if you have mass overload, your retention time is actually a little bit later or a little bit earlier than it normally would be at the peak.
Earlier.
What did you say, Bajan? Speak up.
Earlier.
Yeah, earlier. So that if most of it's moving through without interacting with the stationary phase, and the actual stuff that's interacting with the stationary phase, which remember is the stuff that we care about, is delayed a little bit, then that tailing could actually be the stuff we're interested in. And so, how do you solve mass overload?
Don't put so much on the column.
Put less mass, right? And so a smaller sample size. And so say we were using, for the capsaicin, we were using 20 microliters, we cut it back to 10. Right? This sample cleanup procedure is, well, we did a little bit of that because we did an extraction with our hot sauce, right? We could have just put that hot sauce right on the column, right? It hurts me to think about it because of all the extra goo that's in there. I mean, you saw what kind of solids we filtered out. But if you have a cleaner sample than that, you could still do a sample cleanup procedure that is either preliminary separation. So say you're doing something with antigens, for example, but you don't actually want to run affinity chromatography, you just want to run regular old HPLC. Well, you could just use, they call them solid phase extractions. They look like mini syringes that have a tiny bit of stationary phase in the bottom of them, just 2 or 3 millimeters of stationary phase. You put your sample on there and force it through that stationary phase, and your analyte gets attracted to it. And so then you can separate out everything else that didn't stick, right? And then force your analyte off the column with a second solution, and then run that analysis. And so, that could be an option where you have lots of things that have similar polarities that might be coming off the column close together. And, they're so similar that even changing our solvents isn't good enough. You could do a preliminary separation to help those things clear up. Oops. If you have, this could also remove, if you have any interfering components. If you have some competition for those stationary sites, and one of the things that's competing is not an analyte you're interested in, you can separate it out and then only get the analyte or analytes that you actually care about. Okay. All right. The last thing, and this is related, of course, but is peak fronting. Right? Peak fronting is really, really not common, right? And so this is much less common than tailing. And really, peak fronting only happens in packed columns. Only is a very strong word, right? 99.5% of the time, I don't know. A lot of the time, this happens in packed columns. Right? Right? If you're tailing, some of our sample, some of our analyte is staying on the column too long, right? But if you're fronting, some of our sample is coming off the column too early. And really the only thing that would cause a sample to run off the column very quickly is if that column wasn't uniform all the way through, right? You can imagine, how many of you had an ant farm growing up? How many of you have seen an ant farm? Like sandwiched between pieces of glass? I had one. Those ants will, make these big old tunnels through the sand, even though there's these tiny little cracks, right? You can think about the particles of sand going together. There's a little space between the cracks, not big enough for an ant, right? And so he moves the sand out of the way and makes these big tunnels. And so what happens in your packed columns is that you get these, there's a word for them, but you get these sort of enlarged pathways that have been sort of etched out through the column, and that just happens over time. It just has to do with column age, right? And so you get these larger paths. Remember in GC, we talked about how GC has packed columns, but also has the open bore columns, and those are the more common, right? What we're doing is it's almost the exact opposite of that column deformation where it was blocked, right? This is still a column deformation, but it's now wide open. And so the molecules that find that wide opening go through the column a little bit faster, right? And so they're a little bit ahead of the curve. And so some of those analytes get through a little bit faster. Another issue, so that would be like if we had, so if here was our packed column, right? And for whatever reason, at the beginning of this column, say that we've just had too many injections, right? And at the beginning of this column, there's like this big open space that runs for, I don't know, that looks like 3 centimeters into the column, right? And so whatever analytes happen to find that one little path, well, they're 3 centimeters ahead of everybody else, right? And so before they really start slowing down and interacting with the stationary phase. Right? Another issue could be that the stationary phase, or really the stationary support, that column bed, has started to separate from the walls of the actual, that physical stainless steel wall surface. And again, this has to do with column age. And so you have, over time, they pack these columns very, very well, right? But they don't run them for, 10,000 cycles or something. And so as you keep flowing mobile phase through it, and as they just live through 6 months of vibrations or whatever, there's bound to be a little bit of settling inside that column, a little bit of compression due to the force of that mobile phase moving through it constantly. And so you get some of these issues. You get these more wide open paths. You get this separation from the column wall. And really the only solution for peak fronting is to replace a column. Almost every instance of peak fronting is due to a structural issue with the column. And like most of the time, that's due to age. And so you just have to replace that column. There was one rather cynical site I was looking at in preparing for today's lecture that talked a little bit about how, they say peak fronting is very rare, but really peak tailing is just so bad these days that you have a peak that's fronting and tailing at the same time and it looks symmetric. That's a very cynical view of the world, but that's what one website said. Okay, well that's all I really wanted to finish up with chromatography, this issue of peak asymmetry. There are some special equations out there for determining resolution on asymmetric peaks, but they get real crazy real quickly. And so we're not going to look at those. What resolution do we look for in chromatographic peaks to consider them separated? R has to be greater than or equal to it was a long time ago. It was HPLC.
1.5.
There we go, 1.5. And so you can imagine that if we have very nice pretty peaks, it's easy to calculate if it's 1.5 or not. But if we have peaks that are tailing, it's a little bit more difficult to see where that 1.5 is. And so the peak resolution for asymmetric peaks is not a pretty equation. So we won't get into that. I did it one year with students and they were like, why do we have to know this? But because they are pretty involved. Okay. All right. So the stuff that I want to talk about in terms of potentiometry and electrochemistry, switching gears a good bit here, right? Let me. Yes, I know. Right. So there's no way you can see this. I can barely read it. But this is all of the, not all, but this is the table of standard reduction potentials. And this is, remember, again, I don't know if you can see this. This column is voltage, V and V. Right? This first column, these are all positive voltage. This second, well, I guess the third column, these are all the negative voltages with our hydrogen reaction in the middle. Remember, hydrogen is arbitrarily set to 0. You have to have 0 somewhere. And so hydrogen it is. Do you remember setting up like galvanic cells in 124? Remember all this? I know it's been a while. So we have this difference in potential, and you have one reaction happening on one side of your little salt bridge and one reaction happening on the other side of your little salt bridge. Do you remember this? It looks something like this, right? And so, this is a simple one where you have zinc going to zinc 2 plus on one side and copper 2 plus going to copper on the other side. And you can calculate the overall potential of a cell if you know those standard reduction potentials from the previous slide. The way that potentiometry works and how we use this to actually measure chemical reactions is by knowing what reaction we're looking for, knowing what the cell potential should be, and seeing what it is and calculating that difference. So let me see here. Yeah, this is where I want to be. So in this electrode, this is like a pH probe. Right? Inside, you have your 1/2 of your system. Right? So for pH probes, and we'll get into this a little bit more on Wednesday, but for pH probes, you have this silver chloride system on one side, and of course, we're interested in H+. Right? Well, this glass membrane is thin enough, and remember, H+ is a proton. Protons are T90, right? Because they have no electrons. It's just a nucleus, and it's the smallest possible nucleus because it's just a proton. And so it's that little proton can sort of wiggle across this glass membrane. H+ can wiggle in and out of that glass membrane, and we measure the potential at this junction. And see this here. So here's our solution level. And so we measure, that's our salt bridge. This junction here is our salt bridge. And so we measure the potential flowing from our system inside the bulb to the system outside the bulb. And of course, it's passing through that little junction, that little salt bridge. We're going to go into this in more detail. I just wanted these words to be in your mind before I talk to you in more detail about it on Wednesday. And when we measure that potential difference, we know something about the system because we know everything about the system inside the probe. The only unknown is the system outside the probe. When we looked at E naught, this naught means starts with an S.
The standard temperature and pressure?
Yeah, so standard conditions. And yeah, we will consider temperature. So 25 degrees C. Sometimes we have to consider pressure, especially if it's a gas. So for hydrogen, right, we have to consider pressure, 1 atmosphere. Since we're dealing with solutions, we also need a concentration. What's our standard concentration?
1 molar.
1 molar. Right? And so, again, we know everything about our system inside the probe. The assumption that a lot of these pH probes take into account is that it's 1 atmosphere, which is pretty good. I mean, on a really rainy day, maybe it's 0.97 atmospheres, but that's still pretty good. And that is 25 degrees C. There are some nice pH probes that actually take into account temperature difference, so that you can really, measure this really accurately. But a lot of them just say that it's either 20 or 25 degrees C, depending on the probe. A lot of our glassware and stuff is calibrated to 20 degrees C. And so that's what a lot of stuff is done, even though it's not technically standard. And so if we know the concentration inside, we assume the pressure to be 1 atmosphere, and we assume the temperature to be, let's say, 20 degrees C, then we can work out what the concentration is on the other side of that probe and know something about the pH or whatever it is that we're interested in. Look, on the other side here, we've got a fluoride ion electrode. These are called ISEs, ion sensitive or ion selective electrodes. In all of these cases, you have a very known solution, a very known system inside your probe. The unknown system is outside the probe. And then, of course, the connection between the two is our salt bridge. All right. Again, I just wanted to take these last few minutes today to remind you some of these words, have you see that table of standard potentials. This Nernst equation, we're going to use a little bit more, right? It relates the standard cell potential to the observed cell potential, and it takes into account this QEQ. What do we call that?
Equilibrium constant.
Oh, it's not a constant because it's Q.
Oh.
Is it the reaction quotient?
There we go.
Yeah.
I'm going to call it the equilibrium quotient. But yeah, reaction quotient is A-OK. It's just we know that this is going to be an equilibrium. And Caroline, it is calculated exactly the same way as an equilibrium constant. It's just not necessarily at equilibrium. But this is where we take into account the concentration of our known half of our reaction and the unknown half of our reaction, because R constant, temperature constant, the number of electrons passing constant, Faraday's constant. And so we know everything else. And if one of these two concentrations is a known constant inside our probe, we can always solve for the other concentration. So we will work through a couple examples with the Nernst equation, generally speaking, and then we'll apply it to some electrochemical systems in terms of analysis, specifically on Wednesday. Okay. I will upload my tailing and fronting slides. These slides are part of the chapter 18 packet, and so I'll make sure that those get up as well. I hope you have a good Monday.
See ya.
So long.
Is everything that's going to be up for our project up on Moodle?